air temperature, relative humidity, and pressure are collected worldwide from thousands of weather stations, similar to what you see in the figure given below, and they are processed to produce global weather information. Now, where does the data used by climatologists and weather forecasters originate? Until the arrival of satellite measurement capabilities, all data came from thousands of weather stations located across countrysides worldwide, such as what you see in this figure, and on buoys scattered across the oceans. Today, satellite observations provide 24-hour coverage of the globe, including the continental United States. With the recent advances in satellite technology, we can obtain fine-scale detail of clouds and various weather systems, such as the hurricanes seen in this image. Data originating from both satellite observations and ground measurements are merged through complex computer algorithms, and this information is typically processed and outputted in weather maps, as shown in the following image. On these weather maps, we can determine the location of high and low pressure, the location of fronts, and other large-scale weather phenomena. If we measure and observe these weather elements over a specified period of time, say many years, we would obtain the average weather or the climate of a particular region. So in simple terms, climate represents the accumulation of daily and seasonal weather events over a long time, along with the extremes of weather. Examples of climate variables would be the low and high temperature for a day for a specified area, the average temperature for a year, or even the average global temperature for a year. Therefore, an accurate assessment of Earth's climate relies upon the accuracy and reliability of all instruments used to measure weather data. Now, the features of a site for a weather station must be standardized across all weather stations to minimize the error introduced by particular aspects of the surrounding area. Inconsistencies can be caused by shade from trees, heat reflected from buildings or parking lots, heat added from heating or air conditioning vents from buildings, proximity to a large body of water such as a lake, the type of housing that surrounds weather sensors, and so on. Each of these elements produce what we call a microclimate for a given region. And the error introduced by these differences in microclimates can be rather considerable. In this video, students will learn about the weather instruments used to collect weather and climate measurements. Therefore, by monitoring microclimates using a wireless weather station, students will learn the local factors that must be considered in choosing sites for weather stations. We will now set up our Pasco wireless weather sensor. So as a reminder, the wireless weather sensor is an all-in-one instrument for monitoring complex environmental conditions. It's a very small detector, as you see here, not very large, but it houses several sensing elements within this single unit. And you're actually able to produce 19 different measurements associated with this small device that you see here. Some of the common measurement instruments would include, there's a thermometer there that gives you the temperature of your environment. There's a barometer inside that is electrically used that gives you the barometric pressure. When you attach the wind vane, as you see here, it allows you to obtain the wind speed and wind direction. And there's a humidity sensor on here, which means that you can obtain relative humidity. So those would be the major variables that you can get from here. And then because of the actual technology, you're able to take these variables and use them to obtain other variables that is often used in meteorology. So for example, if you have the temperature and the wind, you can actually compute the wind chill if it's a particularly cool day. Likewise, if you have the temperature and the relative humidity, you can compute what the heat index is, or what we call the heat stress index. Now we will look at the procedure that we're going to use to set up our device. So the very first thing that you will need to do is to connect and to charge. What this means is that your device comes with a USB port cover to the right. And so if you look to the front and then turn around to the back, notice that there's a USB port right there. Now, with that particular package, you're going to have a micro USB cable so that you can connect your wireless device to a USB port or USB charger. Now, just in terms of a background here, if you pull this out of your box for the first time, it will take around 2 hours or so for this to fully charge if you have a good wireless station. So make sure you leave time to charge this completely. Then after you charge it for a few hours, then you're going to turn it on. And as you see, there's a button right in the center right here, and you're meant to turn that on. And when you turn it on, what you will notice is that you will see the GPS light and the Bluetooth light comes on, and it will flash back and forth like so. Now, since it's flashing back and forth, this is meant to tell you that the device is now ready to pick up Bluetooth and is also ready to be connected to the GPS part of the sensor. The next part is once you have it turned on, we're then going to switch to looking at the data collection side of our software. Now, I'm going to go through this in more detail, but the main point here is that you need to make sure that you have Bluetooth capability with your computer so that you can actually use the software. So now we're at the data collection aspect of the software. Now, the software I chose was named SparkView, and SparkView comes directly from the website from Pasco. So if you were to search for the wireless weather sensor, it will give you software that's either SparkView or Pasco Capstone. For this, I'm going to be looking at SparkView. Now, just in terms of a basic experiment, the first thing you want to do is to go to the sensing data aspect here and click on it. And we'll ask you to connect to a device. Now, if you press and hold your device and turn it on, what should pop up would be a device that is connected to your Pasco wireless weather sensor. Now, the 6 numbers you see here is the ID number of your particular detector. So for mine, it is 018690. So if you click on that, it will begin to connect to the actual device via the Bluetooth. And then the next thing it's going to ask you to do is how would you like to proceed? Now, I've already done at this point some original data logging, so I'm going to delete my data from this and move on. But this goes back to the many different variables that you can observe as this goes on. So let's suppose I want to observe temperature, relative humidity, and pressure. Then I will click on those 3 that you see here. And then the next thing that will go is I'm going to go to graph, seen here. Now, right now, the way that this is set up is that you have temperature, relative humidity, and barometric pressure on the bottom. Now, if you wanted to change the units to that, say edit data properties, you can click on that tab, and what's going to pop up would be temperature and degrees Celsius to that. You can change this to Fahrenheit if you like, and the same thing is true for the barometric pressure. You can also change this to millibars, which is the common units that is used when pressure is reported in meteorology. For right now, I'm just going to keep those as they are. Now, right now, this is reading 24.8 degrees Celsius, relative humidity 42.4%. This is reading what is currently going on in my location. Now, once I press the start button, it's now going to start recording that data and placing it on a graph. And as you see, it's just recording this second by second. So you can begin to see changes in the actual temperature, changes in relative humidity, and any changes that are going on with the pressure. Now, what you will see here is that the actual relative humidity is changing a good bit, while the temperature and the pressure is remaining constant. Now, this is something to be expected because relative humidity depends not only upon the moisture that is in the air, it also depends upon the temperature. And if the temperature fluctuates slightly between, say, 0.2 degrees or 0.3 degrees, that's going to have an impact upon the relative humidity. Now, let's suppose at this point you want to stop and record your data. And you can press stop right there. Now, if you go over, you have different sorts of tabs here that can give you ways to set up your hardware as well as other experimental tools. Now, what I'm going to do here is that now I'm going to run an experiment in which I take multiple different sensors and place them in different locations around my building to get different amounts of data. And one of the points here to see is that there are going to be slight changes in all of these variables just based upon where these things are located. Now, for this experiment, I've taken 3 different wireless stations and I've placed them at different locations in the building that I'm currently located. Now, the idea is that the building itself is supposed to be climate controlled. So that means I should expect that I would get the same exact temperature at each location. Now, the question is that what we actually observe? So what we're going to do here is that I'm going to click on temperature for one sensor, temperature for the other, and temperature for the third. And I'm now just going to make a graph. And now what's going to be produced is going to be 3 distinct temperature readings. And now we're going to look at what happens when we run the actual model. In this case, run the actual data that's being collected, and we're going to see if the temperature is the same. So let's press start. And what we immediately see is that the temperatures do not start the same exact way. That one sensor starts 2 degrees higher than the others. So whereas 2 sensors have about the same temperature, around 23.7 or 23.6, another is at 25.6, excuse me. Now, in our case, the only real difference between what's going on here and what's being read here is that I've just placed these at different locations. So it turns out that the top one here, I've placed this at a window, and the second one, I've placed this on a table, and the third one, I've placed this on the ground. So notice that in this situation, just where you place the actual detector is going to determine, in a large sense, what actually the reading happens to be. This is very much analogous to what happens when you take a weather station and place it in different locations. So for example, if I were to take a weather station, place one sensor at, say, an airport, and then place another sensor, say, in the grassy area outside the airport, you will get two very different results. Part of the reason why is because, as we mentioned earlier, anytime you have a parking lot or concrete in an area, you will receive much more reflection from sunlight, and you're going to get what we call a heat island effect, where the concrete is going to cause more heat to be released towards the detector. So that means where you place these sensors will matter in terms of the temperature that is measured. Now for my second experiment, I'm going to use the same three detectors, but now I'm going to examine the relative humidity that's being computed based upon each individual detector. So now I'm going to click on relative humidity for each of the three sensors. Here's the first sensor, here's the second sensor, and here's the third sensor. And now what I'm going to do is to click graph and go through the same process as before. And now we're going to run the experiment. Now, what you should notice here is that the second two have approximately the same results, 42.1 and 41.9. So that's pretty close to one another in terms of results. But notice that the relative humidity is actually lower by 3% compared to the others. Now, why is this the case? This is because relative humidity is not only measuring the moisture content in the air. Relative humidity is also a function of temperature. Now, what this means is that relative humidity will tend to decrease as the temperature goes up. So remember that the first reading here, the first detector was producing a higher temperature, and that means it should produce, therefore, a lower relative humidity. Now, for this reason, that's why relative humidity is not the best variable we can use to examine the moisture content in the atmosphere, because it varies as a function of temperature. But the point here, again, is to say the following. Notice that when your temperature is different, depending upon where the object is located, it's going to affect all of the other results that you will get, such as relative humidity. It will also affect wind chill, and also it will affect the heat index that is computed. Now, I've just made the argument that relative humidity is not the best variable that we can use to determine what the true moisture content is in the atmosphere. Fortunately, our wireless weather sensor does have what is known as absolute humidity. And this is a direct calculation of the moisture content in the air. And it does not depend upon temperature. It's strictly a measurement of the amount of water vapor in the air compared to everything else in the air. So now I'm going to run the same exact experiment. So I'm going to click on absolute humidity for each of my three sensors. So this is the second, and this is the third. And I'm going to run the experiment. So let's click on graph. And let's press start. And now what you will see is that the absolute humidity is basically the same for each of the three sensors. 9.2 to 9.1 grams per cubic meter. So again, this illustrates the point that even though the moisture content may be the same, you can have temperature fluctuations even in something as small as a building. So now imagine this for a city, or imagine this for a town. You should expect there to be strong fluctuations in temperature as you go from one place to another within a large urban area or within a city. And as you have temperature fluctuations, that's going to impact other variables for a given system or other variables for your climate. But for moisture, notice that there's no change whatsoever happening in this experiment. Now for this last experiment, we're going to look at barometric pressure. So the idea here is that we're going to see whether or not fluctuations in temperature in a region is going to affect pressure. So now I've clicked on barometric pressure for each one, second and third that you see here. And now we're going to click on graph. And now we're going to run our data. Now, what you should see here is that notice that the second and third instrument have the same basic pressure, about 759.6 millimeters of mercury. However, notice that the first device, which had the higher temperature, also has the lower pressure as a result of that. Now again, that's not an accidental feature. When it comes to air, pressure is a function of temperature. And what we're beginning to see here is that temperature fluctuations can also affect pressure fluctuations in a local region. So when you put all of this together, what we see is that even in a place as small as a building, you can have temperature fluctuations that can cause other fluctuations in other regions based upon what's going on in your building. This has implications for what goes on in the atmosphere. So to conclude this video, these devices, the Pascal wireless weather stations, are ideal for investigating microclimates, small-scale climatic fluctuations that can happen in your local area. So what I would suggest is to find a location anywhere outside that has some unusual characteristics, especially one that is unlike what anyone else would have chosen, such as the National Weather Service. Now, here are some examples in which you can investigate, and this can be treated as a project over the course of a day or even perhaps over the course of a week. So one, let's suppose you place your Pascal detector under a well-shaded region by trees. Now think about how that would impact the reading of temperature, moisture, and the actual winds as well. You can compare a Pascal detector here around trees with one that is close to a large parking lot, which means that you have no obstructions, you have direct sunlight, and that means you're going to also have a lot of winds that are going to move across the parking lot. You can also choose it to be close to a pond or a lake. In that case, we would expect that there will be much more moisture either going towards the detector or away from the detector. In which case, we'd expect that the absolute humidity would be substantially different here versus, say, in a big parking lot. Think about it being in the middle of an open field. Now, in an open field, you also have direct sunlight coming down, but grass tends to hold much more moisture than, say, concrete in a parking lot. So if you decide to put a Pascal detector near the ground in the middle of a field, you might get the moisture characteristics of the grass, relative to, say, getting the moisture characteristics of a big parking lot. Now, also, there are people who have wireless weather stations in their house. And what they can tell you is that where you put that weather station is going to dictate very much what you get as a reading. So, for example, what would happen if you took a wireless weather sensor and you put it next to the vent of an air conditioner? Think about how that would change your results. You probably would expect to have much different values for absolute humidity and much different value for temperature. Now, if you consider your school, you can do the same basic idea. What would happen if you took your Pascal detector and put it under a sheltered, sunny area on the south side of a building? Think about the sunlight you would receive there versus if you took this and placed it in a sheltered, shaded area on the north side of the building. Think about how those can actually affect the climate and the actual temperature that will be measured. So these Pascal detectors are wonderful to use to measure the subtle changes that occur. And this explains why, in a very real sense, it is an art and a science to find ideal locations to place a weather station, because you want to find a place in which you don't have unusual characteristics, and you want to find a place that will be representative to the whole of your particular region.